This is called a Poincare diagram, so it plots the determinant of A versus the trace of A, and this is for a 2x2 linear system of ODEs. And we've got some typical examples here of all the different types of phase portraits you can get. So kind of on the top left here you have the stable part, the top right you have the unstable part, the bottom half you have the saddles, and then all the different phase portraits you can get. So there's stars, there's nodes, there's degenerate nodes, there's spirals, there's non-isolated fixed points, there's centers, there's kind of a silly one that's a constant, and then there are stable and unstable counterparts. And so let's just get right to it. So we're going to do an animation of how these kind of morph into each other as you change the elements of the matrix. So we're going to start out at stable spiral. We're going to get close to the boundary. We're going to become a center. Then it's going to transition into an unstable spiral. Then we're going to have a change in direction. We're going to go towards the boundary. That includes stars and degenerate nodes. Then we'll go into the unstable node region, and we'll come back and revisit the same point for a degenerate node before it was a star, and we'll continue through, and we'll get to unstable non-isolated fixed points, and then we'll get into saddles, and that's where the animation will end. So without further ado, let's take a look. I've put the Poincare diagram on the left here, and here's the path outlined in a dotted line. So we're going to go up, down, up, backtrack a little, and then eventually make our way to saddles. So right now we're in the stable spiral region, and you can see here, right, the trajectories are going into the origin from the direction of the arrows. So let's go ahead and start the animation. So as we're getting closer and closer to the divider, which is centers between stable spirals and unstable spirals, the trajectories are still rotating at the same rate, but they aren't as attracting to the origin anymore. And eventually they're going to get pretty dense, so I'll stop the video there. And so here they're quite dense, and they're overlapping a little because of initial conditions just happen to line up with other ones. And so in the next bit, between here and 0, it gets really, really dense, so it actually gets quite difficult to graph. So I skipped a little bit. And this is a stable spiral. The center is attracting, and this is actually one spiral. This is how dense they're getting. It's because they're not contracting into the origin as quickly anymore. And in fact, there's this giant filled circle in the middle because it's going so slowly into the origin that the lines are overlapping with each other. But if we just nudge it a little more, we're going to get to centers. And so this one, you've changed from a stable spiral, which was still going into the origin, although very, very slowly, to it neither goes away from the origin or it gets closer. So when you go around in a circle, when you come back to where you started at the same angle, you're at the same distance from the origin, and just keep going around and around. So that almost circular spiral actually became circles. Now we go a little bit further, and we're going to become an unstable spiral. And again, this is unstable, very difficult to trace out yourself, but if you do manage to follow one of these around, you'll see that it's actually going away from the origin. It's unstable. Then I'm going to skip a little bit because it's quite disorienting to watch. So now it's unstable. You can probably tell with your finger now that these are actually spiraling outward. The rotation rate and the rotation direction, so this way is clockwise, that stay the same. But now we're going to keep going, and we're going to get to another unstable spiral right around here. And as you can see, the trajectories keep getting more and more repelling from the origin. The arrows kind of go the opposite way now. So now, to go from the next step here at the unstable spiral to here, I've changed the arrows so that they don't get bunched up so much, they don't get in their way. But we're going to transition from an unstable spiral, and what's going to happen is kind of the rotation rate is getting slower and slower. So the spirals are essentially straightening out. And as they straighten out more and more, they're eventually going to become an unstable star. And then the eigendirections here is every direction, and so that's why every direction here is red. Every direction is an eigendirection, and they're all equally preferred to go out of the origin, unlike nodes. So now from here, we're at the unstable star. We're going to become an unstable node immediately after leaving this boundary. And you can see now a preferred direction showing up along this eigendirection horizontally. So now we get to this point near the end, and because you're mapping a four-dimensional space, so the matrix A has 4 elements you can fiddle with, right? The top left, the top right, the bottom left, the bottom right. It's projected onto this two-dimensional space, mapped onto this two-dimensional space. And so we're actually going to be changing this phase portrait and we're changing elements of the matrix, but we're not actually moving from this dot. And what that's going to do is it's going to rotate one of the eigendirections. And we'll get to, I think, about diagonal. Yeah, and then we're going to start changing another element in the matrix, and we start moving again on the Poincare diagram. We're going to get back to the boundary, but this time the eigendirections line up, and now we have an unstable degenerate node, where there's only one eigendirection, where there was a multiplicity eigenvalue with multiplicity 2. But now we're going to keep going past that, so the eigendirections are going to separate again. And we're going to make our way to non-isolated fixed points. Right, so I don't have any arrows on this eigendirection because the eigenvalue in that eigendirection is 0. So you actually have all the points. You either stay on this line forever, or you go away horizontally from that line, from that eigendirection with no arrows. Now we're going to have one positive, one negative eigenvalue as we go into the saddle region. And then it gets more and more like a saddle, more extreme as we continue, and eventually we stop. So that was cool, but what exactly happened, and how did I make that? So again, this is a Poincare diagram. We are traversing all the different phase portraits you can get in a 2x2 linear system of ODEs, and the numbers we can play with right on the matrix, the elements of the coefficient matrix A, B, C, D. And so determinant A, trace A, we're going to plot those. First off, why are those useful? So determinant of A at 2x2, that's AD minus BC. It has a nice relationship with the eigenvalues, though, is the determinant of A is the first eigenvalue times the second eigenvalue. In the trace of A, that's not as common, so that's actually the sum of the elements along the diagonal. So in this case, it's A plus D. And that has a nice relationship to the eigenvalues as well. The trace of the matrix A is lambda 1 plus lambda 2. And so using that, there's some clever ways you can figure out if you're going to have complex eigenvalues versus real, and that transition, that boundary, happens to be when the trace of A squared is equal to 4 times the determinant of A. And so that's this parabola here. And so kind of inside the parabola, you end up with stable spirals, unstable spirals, and centers. And then outside, you end up with stable and unstable nodes. On the boundary is where you get stable stars, stable degenerate nodes, the kind of silly constant solution, then unstable degenerate nodes and unstable stars. And then as well, so if you have the eigenvalues are one positive, one negative, meaning you're a saddle, then that's going to show up in the determinant being negative, so the whole bottom half here is saddles. And then separating the saddles from everything else is the stable non-isolated fixed points, because you have a 0 eigenvalue and either a negative eigenvalue or a positive one, and then you flip to one positive eigenvalue, one negative eigenvalue, and you get into the saddle node region. So to kind of dive deeper here, we're actually going to look at the path we took, and we're going to look at the matrices as they're changing and how you end up with the different solutions and how those solutions are changing, and also how things like staying at this point 4 can occur when we're changing elements of the matrix, and also how we can get two different phase portraits. You know, we had an unstable star and an unstable degenerate node, even though we were at the same point in the Poincare diagram. To sum up, the reason for that is we have these 4 parameters to change, A, B, C, D, 4-dimensional, but this is only a 2-dimensional plot. And so you can end up with the same matrix, actually many matrices going to the same point. So let's go ahead and look at kind of the same video, but now we're going to look at how the matrices are changing and also how the solutions change. So here we're starting off with the same stable spiral we started with in the previous animation, but now instead on the right, instead of the Poincare diagram, I've got the matrix and the solution, and also the parameter that's changing over time that's going to alter the phase portrait. So in this one we have the stable spiral. I call the parameter g, and the matrix I'm using is g1, negative 1g. And so that g is controlling the exponent on the e to the gt. And so if g is negative, that's going to be stable. But if g gets closer and closer to 0, then it's going to be less and less contracting into the origin. It's going to be less and less attracting. And then here, right, this is from the complex part of the eigenvalue that occurs in this case. So you have these two vectors with sines and cosines. Let's go ahead and take a look at that. Right, so g is decreasing. The rate of rotation is staying the same because we still have cosine of times 1t and sine times 1t. but the attraction into the origin is getting less and less because we're getting close and close to 0. Eventually I'm going to stop it here. This number happens to be -1/10 for G. And so by the less attracting, by which I mean by the time you go around one time, you don't get that much closer to the origin. And so this just keeps happening more and more. The attraction to the origin, how fast you're going into the origin, gets slower and slower. Then we're going to go to G is -1/100th. So again, this is a stable spiral. If you very, very carefully trace this, you'll find that they're actually going into the origin. And G is just on the cusp of becoming 0 because it's -1/100th right now. And then skipping into 0, you finally get no attraction into the origin anymore. So by the time you go around, then you end up exactly where you started. And that shows up because we have G now is 0, and I have e to the 0t here, which is just 1. And so, right, if you go around one time, cosine and sine, they're periodic. So by the time you go around by 2 pi, you end up exactly where you started. And so now everything is a circle. It's on this boundary between being a unstable spiral and a stable spiral. And so now we're going to transition just a little tiny bit to G is +1/100 and become an unstable spiral. Again, very hard to tell, but once you go over that boundary, you become an unstable spiral. I put my e to the gt back, and now by the time you go around once, you're actually going to be a little bit further away. Then we're going to skip to +1/10. So here you can actually trace that with your fingers, right? So that you can actually see this is going to be unstable. The spirals are going outward, even though they're still rotating clockwise, they're going outward now. Then we've got our animation as G goes from +1/10 up to G equals 1, and the origin becomes more and more repelling, and so the spirals kind of uncurl more. And they'll uncurl the most by the time they get to G equals 1. So at this point, we're going to change now. We are used up our G, and we're going to change to a new element that we'll change in the matrix, and use this one called W. So W starts at 1, it's going to go at 0. So G ended at 1, and this was 1 before, so now I'm fiddling with W. And W actually controls the rate of rotation because it's inside the cosine and sine functions. But we're going to have a constant repelling force from the origin because we have e to the +1t here. So if we let that play out, if the rotation rate gets slower and slower, that ends up just really uncurling the rotation, right? The rotation gets less and less, the lines are becoming straighter and straighter. And eventually when we get to W equals 0, there will be no more rotation. And so right here we had cosine, you end up, if W is 0, then you had cosine of 0t, that's 1, and then this one I think was negative sine 0t, and then sine 0t, cosine 0t, so you end up with this situation. And now every direction is an eigendirection because the matrix is the identity. If I plug in 0 for W here, I get 1, 0, 0, 1. And so this is an unstable star from uncurling that unstable spiral. So next we're going to fiddle with this variable k. So right, we had 1, 0, 0, 1, k is starting at 1, and we're going to go from k equals 1 up to k equals 4. And what that's going to do is immediately after going away from 1, we're going to end up with 2 distinct eigenvalues, because right now they're both 1. And then as the eigenvalues get more and more different from each other, we end up with these preferred directions to go. And so right, this is, as time goes to infinity, you're going to follow more and more this eigendirection. This eigendirection is the e to the 4t eigendirection, or e to the kt. Then we're going to stop for a sec, and we're going to change another parameter. And so this one, we're actually not going to have the trace or determinant change while we're changing b, because right, the determinant is ad minus bc. And right, no matter what b is, I'm going to end up with 1 times 4 minus b times 0. And so it's always going to be 4. And then the trace as well is going to stay exactly the same. So we end up with just 1 plus 4 is 5. And so what's going to happen here is our eigenvalues don't change. We still have 1 and 4 the whole time, but our eigendirection is going to change. We'll see that happen from 0 to 2. You can kind of see everything slanting over. By the time we get to 2, then we're going to introduce a new parameter. This one's called r. And this one is now going to change the determinant and the trace, because we have 1 times r minus 2 times 0, so our determinant is always r, and our trace is 1 plus r, so that's always changing. We're also changing the eigendirection here, so we have our e to the rt, and that's going to actually get us to an unstable degenerate node. That's going to happen at this value of 1 here. So we're going to have these eigendirections get closer and closer together until eventually you end up with them on top of each other, and you have this very different solution now. You have, right, e to the t, and there's a multiplying by t in here, because we had an eigenvalue. This eigenvalue happens to be 1, but it has multiplicity 2, and there's only one eigenvector. And so you end up with this kind of weird portrait, and you can kind of see it though when it was going in. These lines were getting more and more curved around, and eventually when they lined up, that curve just stayed there. And I think if you take some limits as the value of r goes to 1, meaning you end up with the same eigenvalue in both cases, and sorry, for both of these, then you can end up getting this t as a limit. We're going to continue past through that, and we're eventually going to get to non-isolated fixed points. And so eventually the eigenvalues, they're different now, but they got close. One of them got closer and closer to 0. And when it finally got to 0, then you have these horizontal directions. That's the direction they travel, unless you start exactly on this eigendirection with eigenvalue 0. And so now we've gone from, we had 2 positive eigenvalues, so that was going to be an unstable node. We got to 1 positive eigenvalue and 1 zero eigenvalue, and now it's going to change to 1 positive eigenvalue and 1 negative eigenvalue as we pass through that boundary. We become a saddle immediately, and then you just kind of continue as a saddle, and it gets a little more extreme in one of the eigendirections. But that's that. So you might want to go back and watch the video again and see, how these are lining up. For instance, looking at how the matrices were changing as we went through here, right? We changed an element of the matrix. We were moving through all the way, got to center, got to this unstable spiral. We went down to here. We were first an unstable star, and then we left, and we got to 4, and then we were actually able to change the elements of the matrix. So it was A, I think the parameter B was what we were changing, and then 0, and then D. And because you're mapping essentially 4-dimensional space, right? We have 4 numbers to choose from here to a 2-dimensional plot. Lots and lots of matrices actually correspond to that. Because this C was 0, we could change this element without moving. And then we were also able to go backtrack over ourselves. Even though the matrices are different, they map to the same point in the Poincare diagram. We're actually able to get an unstable degenerate node the second time we passed through this point, when before we had an unstable star. And then you continued on, right? You got to non-isolated fixed points, and finally you got to the saddle region. So hopefully that gives a little more intuition, and also how these actually change into each other. It's nice to have an animation to see how it slowly occurs, and how these are all related.